So this is an example of the circuit breaker pattern. Circuit breaker pattern was one of the stability patterns that Michael Nygard documents. And one of the, I guess, most common uses of it, or places, examples where you might have seen it, is the Twitter fail whale. Right? What happens when a system gets too many requests too fast? You would like some way to break the circuit, to say it's under too much load, and I want to disconnect from the actual back-end service, and I want to start returning trivial responses on the front end to take load off that server and give it some time to recover. That make sense? I mean, that's a pretty important distributed pattern. And it's something also you might see inside a multi-core system. So in order to have a circuit breaker, what we're essentially doing is saying, I've got some kind of a service, and I'm going to create a circuit breaker as a proxy out in front of it. So the service actually doesn't even have to be aware that the circuit breaker exists. The circuit breaker is just a wrapper pattern for the service. To the outside world, the circuit breaker is the service. That's the reference everybody else gets. They don't actually have a reference to the service. And any request that comes in to the service is going to have to go through this circuit breaker, and it can monitor how long it takes to respond to the request. So I'm going to create a customer here, send a ping request to the circuit breaker as the service. And that's going to come into this logic here. We'll skip over the administrative messages here because this is what we're going to focus on as the code here at the bottom. And what I need to do here is there's several pieces to this. When the circuit breaker receives a message, it's going to create an instance of a timer. And this is, again, sort of an example of that work order. The timer exists just for this particular request. So there's an actor that just represents the potential timeout of this particular request. That one has a lot of connections. Now I also create a reply. I create a reply actor, and it's got all kinds of links. The reply link needs to know who the timer is, because that's the authorization key that says, I've timed out this request. It needs to know, it has to have a reference to the authorization key for administrative requests, because we don't want just anybody making administrative calls into the circuit breaker. So it has to be given that capability in an object capability sense. It has to remember the circuit breaker that it's going to talk to, and it has to know the customer that's supposed to get the reply. So this is a pretty complex little work order that's handling the actual response. And now this is going to be the customer that actually gets passed to the service. Notice that the circuit breaker is now essentially out of the loop, because the reply is going to come back to this reply actor instead. All right. And of course, the last piece of it is it's going to send a message on to the service with the customer, like I said, as reply 1. And the last piece, the last send here, is sending a delay message to the timer service saying, after this delay, I want you to send that timer as a message to the reply. Again, the timer is an authorization token that says, I can uniquely identify that this particular event happened. So let's posit what actually will happen and which message would get delivered first. In this case, we're going to say, well, the ping message. The service responded in time, so the ping message happened first. It gets processed by the service, trivially returns a reply pong to the reply customer. I'm not showing the service here, but I think that's pretty evident. Okay, so I send a pong message back to the reply. And the reply is this code here. And it essentially has two cases. The first case, let me scroll it up so you can see better. The first case is if the reply is a reference to the timer authorization key. If that happens, a timeout happened. If it's anything else, then it's just a reply message, and I don't have to care what it is. And I can just send it on to the original customer, and I can notify the circuit breaker that it worked. So that's what I do. I send a Pong message onto the customer. I send an OK, which has the admin key on it that says this is a legitimate administrative message. Nobody else has access to this except the circuit breaker and whoever the circuit breaker gives it to, in this case, to the reply. And the reply now becomes inactive. It becomes sync. Sync is a behavior that receives any message and throws it away. Okay? Now, why do we send a message back to the circuit breaker? Because we want to monitor successes and failures. That's what the circuit breaker is doing. So if we get a number of failed requests, we're going to break the circuit. If we get a successful call, it resets the circuit breaker, and we say, oh, this system's fine, it's responding in time, so we'll let other requests through. Okay? So this is basically telling the circuit breaker, hey, it worked. That request is fine. And it receives that notification asynchronously to the customer receiving the answer that he wanted, because the reply took care of all that. Now, the sync is still not garbage, because the sync, and neither is the timer, right? Because the sync is now the customer for this delay message that the timer has, that the delay service has. And after the timeout happens, it still could fire a message off to that actor, right? So any message that still has a reference to an actor means that actor is still potentially alive. We don't want it to do anything, that's why its behavior has become sync, but it still exists in the system. Okay? So what I showed first here was the processing of the OK message. It didn't change the state of the circuit breaker, which says that I have 0 failures and 2 is the maximum. That's what the 0 and the 2 represent. Delay, after its timeout, sends the fail message to sync, which is really just a reference to the timer. And the timer, being sync, the reply actor being sync now, flatly ignores it and no longer has any references, so it and the timer are both garbage. Okay? All right. Second customer comes along. I'm going to step through this a little more quickly. We set up the same kind of a reply structure, the same kind of a timer structure. We sent the ping onto the service. And this time the timer responded first. So the fail message is now queued for the reply actor. In this case, it receives that message. And so what happens when reply receives the timeout message? It sends the administrator a notice that says, it sends the circuit breaker an admin message saying that this delivery failed, it timed out, so that the circuit breaker can up its failure count, and then it sends a fail response to the original customer. So instead of getting Pong, it gets fail. Now, the nature of fail messages and rejections and things like that can be structured. I've simplified it here by just tagging it to show how it might work. Now, since it's processed the timeout, it's immediately also becomes sync. Because now I don't want the actual reply, if it actually ever does come back from the service, to make it through to the original customer. They'd get 2 replies. And we've already failed the request. So the administrator or the circuit breaker receives that fail message, and that fail message bumps the failure count by 1. Pretty trivial. The service does eventually reply, where it's promptly ignored by the sync, and we've handled that case. All right, so I get another instance coming in. And I get a fail message, and the service replies. Okay. So now both messages are in transit at the same time. At this point, it's non-deterministic in the actor model which message is going to be received first. But it doesn't matter, because the behavior is essentially the same. And that's what I wanted to show, is that even if both messages are queued, waiting to be received by this actor, the behavior is still correct, no matter which one gets processed first. I don't have to be fully processed before the other message sort of shows up. So what happens in this case is the fail message gets processed, so the Pong message is still queued for sync for the actor that was reply and has become sync. The fail goes back to the customer. failure count goes to the circuit breaker, receives Pong, throws it away, no problem. So now I have 2 failed requests. And I've just sent the notification to the circuit breaker. When the circuit breaker receives this notification, it becomes a different behavior. And I needed to represent this behavior in a very small number of characters here. So I represented that with a -2, saying my limit is 2 and I've exceeded it. So I've now become the open behavior. So when a circuit is closed, it passes messages. When it's open, it's broken. Okay? So what I've done now is I said that I've received too many fail messages, so instead of staying closed, I've become open and send a message to the delay that says, I want you to send me back a reset after some amount of time, because that's the time I'm going to retry the process and let further requests go through. So this is the back-off time that says, how long am I going to wait before I retry establishing contact to the service? So now the behavior of the callback is this open behavior. And along comes a 4th customer. Move some of these out of the way. If you look at the open behavior, what's going to happen is it's really going to be only looking for the reset admin message. Any other admin messages are ignored. And the message that says that it's getting a request from a customer. But if it gets a request from a customer, it's not even going to bother sending it on to the actual service. It's not going to create a timer. It's not going to need to create any of those things, because it's just going to return the fail whale immediately. So with extremely little processing, the circuit breaker just stops that process right away, sends a reject message back to the customer, and it's done. Now eventually, of course, the delay expires, and the response message, the reset, ends up getting sent back to the circuit breaker. That sends the circuit breaker's state back to closed, where it took the fact that it can handle 2 failures now, resets that count to 0, and says, okay, I'm going to start the counts again. At which point I could process a message from a 5th customer, go through the steps, and eventually end up with the same kind of a success. And the circuit has been reset. Now, Michael describes a half-open state for a circuit breaker as a 3rd state in the higher-level state machine, which basically says that when the reset comes, instead of setting the retry or the failure count to 0, I set it to 1 less than my threshold. So the half-open state is ready to trip again on the first failure. Obviously, that behavior would be very trivial to implement here. Depends on how you code the response to the reset message, whether you set that count back to 0 or what your policy is. And those are some of the things that you might parameterize about the way that you would use this behavior. All right, so the patterns that this one uses, clearly there's state machines going on here. We're using wrappers and proxies to both wrapper customers and responses, coming both directions, adding information as it's being passed back and forth. We're using the authorization keys to identify timeout messages, to identify administrative messages. So, because the circuit breaker is a public interface, right? The circuit breaker represents the service. It's going to be, a reference to this is going to be passed all over the place. So we have to make sure that its protocol, when it's receiving these administrative messages, that they're properly authorized. So this is a good reason for using auth key in that case. And we're using work order, right? The reply with all of its connections is the work order that says, I'm either going to receive an actual reply or I'm going to receive a timeout, and I'm going to coordinate sending the right administrative messages in either case and forwarding the response onto the customer.